Right, so in this video I'm going to do the half-life problems on the worksheet that I gave you, but I want to start off with just a visual of what a half-life is. That might help some of you if you're having a little bit of struggles with this. If you are already comfortable with this, then please just skip this and go straight on to the part you want to hear about. But I've got a graph here, and if you look at what it is, I've got on this axis what my amount is. And so I'm going to do a problem that starts at 100. And you could do it with 100 grams or 100%, whatever you feel like. And then over here on this axis is my time that passes. And if you think about a half-life problem, when we deal with amounts, like we've been saying, we've got two types of amounts that we're looking at. One is initial amount, right? And I'm going to label that my 100 since I already said that was how he's going to start. And then the other one's the final amount, and we'll see where we end up with that. So there are two amounts, initial and final. And then we also have time, and we've got three different measurements that could be about time, couldn't we? One could be about the length of a half-life. How long is a half-life? And in this example, I'm going to choose all my major grid lines, which are completely evenly spaced, to represent my half-lives, because half-lives are always the exact same length of time, right? So I'm going to say, here's my half-life, and every other half-life is exactly the same span of time. The other thing that I count when I'm figuring these questions out is how many half-lives are incorporated. So let's say that my ending point is going to be here, all right? Then I'm going to say this is my total duration. And then I can count up 1, 2, 3, 4, 5, 6. So I know I've got 6 half-lives that are going on in this process. Okay, so let's look at how they decrement, because this might be helpful. All right, so I start off with 100. I know I'm going to lose half of that in my first half-life, and so I've got my 100 going way down to 50, okay? In my second half-life, I lose half of 50, so my 50 is going to go down to 25. And gosh, you see the slope of the curve really starting to change, don't you? So I lost a tremendous amount, 50%, and I still lost 50%, but it's of such a smaller number, and we just see this trend increasing as we go down. So after the third half-life, I'm probably not going to do this exactly right, but you'll get the picture. I'm going to be there at 12.5. After my fourth half-life, I'm going to be down there at 6.25. And then after my fifth half-life, I'm going to be down at 3.125. And then after my last half-life here, gosh, I'm way down at that 1.5 level. Okay, so every half-life, we're always losing half, but the number is slowly getting so small that our trend line has sort of banked out on us. So that's the graphic to keep in mind as you work with half-lives. So now let's go and let's look at the problems. Okay, we did this one in class, but no, I don't seem to be really in focus. Let me see if I can improve that a little bit. Yeah, that's better focused. Oh, it almost does that. Let me go back. Yeah, okay, that looks pretty good. So let's go now and look at this. So with any problem, of course, what we're going to do is we're going to identify those 5 variables, which ones we have, which ones we don't have, and which ones we need. So I see that 25% is my remaining. So, and as you know from class, when I see that I've got a remaining in percentage, I automatically know that I began with 100%. So that was my beginning number for amounts. So both of my amount numbers are present. So let's see how my time is. I've got a half-life number, and that is 5,715 years. Okay. Let's see, do I have anything else? No. And do I have, so what I don't have is the number of half-lives, and I don't have total duration of time, right? And what I'm asked to find is how long ago. But I can see that if I don't have the number of half-lives, I've got to figure that out in order to figure out the total duration. So how do I do that? Well, do you remember our formulas that we used to work with? Okay. Hold on just a sec. Okay, I took a break and wrote out my table, because let's do it first the table way, because that can be the easiest way to get a handle on this. So, hope you can read my writing. I have, after this number of half-lives, I have this amount, and it represents a duration of this many years. So remember we said that when we do our tables, we always start with after 0 half-lives to get our starting amount, which is 100. I don't need to put the percent in there. It'll be all right without that. And that 0 years have passed, right? Because no half-lives have passed. So there we go with that. After 1 half-life, I have 50 left. After 2 half-lives, I have 25 left. And look at that, 25% remains. So I didn't even have to go very far on this. So my total number of years per individual half-life, after the first half-life, 5715 years have passed, and after the second one, 11,430 years have passed. So there I am at my answer. So that's a nice, easy way to do something like that. But some of you are saying, good enough, but let's go ahead and let's do it in a more mathematical approach. What would that look like? And if you remember, what we said was that if you have the initial amount, what you know is that every year, every half-life rather, it goes down in half. So I have half of the initial amount after 1 half year. Then that means that if I have more half-lives, if I have more and more half-lives, whatever the number of half-lives is, that's how much that initial amount is going to go down. So I represent that as 2 to the n, where n is the number of half-lives. Okay? And at the end of that, that initial amount, for however many half-lives I'm calculating, is going to be equal to my final amount. Right? That makes sense. However, in this problem and many problems of this type, one thing that we don't know is this n, right? We have the initial, we have the final, we just don't have the n. And so what we've got to do is get n, first of all, up into a numerator. So I'm going to multiply both sides by 2n, and this side by 2n, 2 to the nth rather, I should say. All right. And now I've got it up in my numerator. I still don't have it isolated, do I? So I'm going to have to divide both sides by my final amount. This gets a little messy. And then final amount, of course, is canceling out. So now I've got 2n is equal to my initial amount over my final amount. Okay? And then I look at that and say, well, I've got those. My initial amount is 100. My final amount is 25. And so that number is 4. But remember what 4 equals. 4 is equal to 2 to the nth. Okay? It's not, this is not my number of half-lives. This is my computation I have to do next to figure out 2 to the nth. And I just say 2 times 2 equals 4. So my number of half-lives there for n is 2. So n equals 2 for my number of half-lives. And that's exactly what I saw here, was I have 2 half-lives. And then from there, you would just do that final calculation and say 2 times 5715 equals 1140 years. and you're done. So you've got two methods to calculate just about everything that we do in this particular unit. All right, now let's go and look at this one. What data do we have? Well, we've got our starting amount. I guess I said beginning earlier. So it's 68 milligram. All right. How much remains? So my remaining is my question mark. I don't know that. Let's look at what we have for our time stuff. So my half-life is 12 hours. Okay, how much remains in the patient after 4.0 days? So that's my total duration. All right, but again, I do not know my number of half-lives. Now, do I need to know my number of half-lives? Yes, I do. All right, but I have a little bit easier way to get that during the data. I'm going to convert my days into hours, so I'm going to say 24 hours per day times 4 days. Oh, look at that. It's 100 hours exactly. That's nice. All right. No, it's not either. What am I thinking? It's 96, right? Yep. All right. So it's 96 hours total duration of time. All right. The next thing I have to do is now I've got my total duration. Now I'm going to go in and I'm going to say what my half-life is, and that is half-life is 12 hours. So 96 hours divided by 12 hours will give me my number of half-lives. 96 divided by 12 equals 8. So I have 8 half-lives. All right. And then how much remains in the patient after 4 days? Now, if I wanted to at this point, I could just do my table, right? It'll be a long table since I have 8 half-lives, but I could definitely do that and work through that. And I would just use the exact same process that we had up here. Another way that I could proceed from here, of course, is to involve my formula, right? And what I would do for that is I would say, okay, I would go ahead and say what is 2 to the 8th. I would use my calculator to do that, and I would say that that is 256. So I've got 256 hold on. All right, my neighbor's mowing right now. Wouldn't you know it? Okay, so I would ask you at this point to remember what our formula is, right? Remember our formula is initial amount divided by 2 to the nth for the number of half-lives equals remaining amount, right? That's the formula we have to memorize. Okay, and think about this. We've got our initial amount. It's 68 milligrams, right? And 2 to the nth, we've already worked through that, and we know it's 256. Okay, now, so all we have to do is the math on that, and we come out to 0.2656 milligrams. So it's a really tiny amount. Does that make sense? Well, if you remember our little sheet that we came up with, yeah, that things really, especially we only did 6 half-lives here. So it makes sense that after 8 half-lives, we would really have an infinitesimal amount compared to what we started with. So that's good. Now, let's do another problem. U-235 waste product, half-life of 703 million years. How many years? Well, 1/8 of its initial amount remained. Okay, so here for amounts, we have our starting amount, or beginning amount, I should say, okay, is 1, and our ending amount is 1/8, right? We could do it that way, and this will be easier actually. So that's our amount data. Let's look at what sort of time data do we have. We know our half-life. Boy, that's a half-life for you. 703 million years? My goodness. Okay, but we don't have total duration, do we? No, we do not. And we also don't have the number of half-lives, do we? All right. So, but what we do have is very, very interesting. And again, we could do this via a chart. But I'm thinking you already know how to do the charts, so I'm not going to do that. I'm just going to do the math on this particular thing. And I'm going to take a shortcut too, because I see here the way they've got it done, and that 8 works into my 2 by 2 by 2 perfectly, right? In that, if at the end of my time frame I have 1/8, 1/8 is equal to 1 over 2 times 2 times 2, right? 2 times 2 is 4, times 2 is 8. So I know right there that since I only have 1/8 left, and it always follows this brilliant progression of having itself, that 3 half-lives have passed. So my n on my half-lives equals 3 half-lives. Okay? So now that I know that, all I need to do is say, if I'm trying to get how many years of total duration are there, then all I need to do is take my number of half-lives and multiply it times the time of 1 half-life, which is a whopping 703 million years. So I end up with 2,115 million years that have transpired. So I guess my point in this is you've got several routes you can use to do this. So look for the easiest route. You could also go back and do your table or matrix and come up with the answer that way. All right, final problem. Radium has a half-life of 11.4 days. If a patient receives that dose, how long will it take it to decay to that? And they didn't have grams there, but they could have put grams in there, right? Because there it is there. So on amounts, I've got both pieces of data, don't I? I've got my starting amount, 0.024 grams, and I've got my ending amount, right, of 1.5 times 10 to the negative 3 grams, okay? And I could also do that as 0, let's see, 1, 2, 3, okay. So I could do 1, 2, 3. So there I am on that, grams. All right. Next, I look at what data do I have about time. The only thing I have about time is half-life, 11.4 days. All right. What do I not have? I don't have the number of half-lives, and I don't have total duration either, right? So when I think about my formula that I had, what should I do next? I say my end amount equals start amount to, and I'm going to just put n there for my number of half-lives, all right? So can I use this to figure out what I have so far? Yes, because I've got my end amount and my start amount, don't I? So, and I know that I can manipulate this, and remember how we manipulated it in the past, so I'm going to go straight to there and say 2 times my number of half-lives equals start amount or remaining, right? Okay, and or final amount if you want to call it that, whatever. All right, and that I can now populate this, right? That I've got a start amount of 0.024 grams and an ending amount of 0.0015 grams. And that when I do that, I come out with 16. Okay, now think about what this is. Again, this is 2 to the nth. So 16 is not my n number. It's my total computation when I do 2 to the nth. And therefore what I can do again is the finger plan, right? 16 divided by 2 once is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. And then I've got one remaining 2. So I've got 4 half-lives involved. All right. Now, I'm almost there, right? I've been asked for total duration. So now all I have to do is take my number of half-lives, which is 4, right? And multiply by 11.4. And I come out with a total of 45.6 days. So the thing that we need to do to master these problems is memorize that formula. I think once you do that, and if you understand how to manipulate it, the rest of this makes sense and you can get through it. And of course, you can always double check yourself and do charts as well. That'll help you out as well. All right, so that's that. Now I'm going to just real quickly do the nuclear equations chart. All right, so let's get that on the road. So now before we were always doing alpha problems, we were always doing beta problems, and here we've mixed it up, haven't we? But we can look at this and say this is helium, right? And therefore I know this is going to be an alpha problem. I can look at this and say this is definitely going to be a beta problem, right? And I can look at this and say I'll do some math and figure out that. Look at that, that's a gamma problem, isn't it? All right, here again I've got an alpha. Here again I've got a beta, all right? And I'll figure these out. Here's an alpha again, right? Whoops, I made it the wrong way. A little dyslexic. And here, my goodness, we'll look at that and figure that out too. All right, so now let's go in and let's do the math and see what we can find. We know that we're always going to end up with the exact same numbers across our reactants as our products, and therefore 234 equals 4 plus 230. So my top number is 230 there. 91 equals 2 plus 89. So we're going to go back later to our periodic table and look at how to find out what element 89 is. All right, let's go down and do the math on this one. 244 doesn't change. 94 equals -1 plus 95. And that makes sense, right? We know for a beta problem, a beta equation, we're always going to end up with one more proton in the element that we end up with than the element that we started with. All right, let's look at this one. I'm at 89 here, and here I'm at 90, so this has to be -1 here, right? Because my sides have to equal. 228, 228, 0. This looks like this is a beta problem, right? All right, let's look here. 232 to 228, there's 4. 90 versus 88, there's a 2. And therefore this is an alpha problem. And that's helium there, right? Okay, let's look here. My good old little gammas, they're nice because they don't really change anything. Right, that's just a gamma reaction. All right, let's go down here. 210 minus 4 was 206. All right, 84 minus 2 equals 82. And we'll look that up later. All right, here I've got a beta reaction. So my 218 is preserved. Right, 86 minus 1 equals 85. All right, 243, 243. This has got to be 0. 95, 95. This is 0 as well. So this is a gamma problem, right? There's where I did my horrible alpha, my dyslexic alpha. All right, 234 plus 4, 238. 90 plus 2, 92. All right, now let's look at this one. My first clue is I've got something already here, but something else is here as well. All right, so let's add these up. So I've got 235 here. How many do I have here? 134 plus 100, so I'm at 234. And then there's 2 ones, so 235, 236. So this is going to be a 1. All right, let's look here. 92 equals 54 plus 38 equals 92. All right, so it's 92 here. So this particle has a 0 here. And therefore, this mass of 1, charge of 0, this is a neutron. So this is actually a fission reaction here. All right, fission reaction. Okay, now let's go. Oops, I didn't get out my periodic table. Hold on, let me pause. All right, if you are doing these on a test at any point, just remember to come back, because this looks very done when you first look at it, and then you realize, holy cow, there is not an element there. So we're going to look for element 89. So we know that they're all down here somewhere, and I see the 88 radon. I go down here, and it's actinium. So I'm going to put an AC. Okay, here's element 95. That's really low on the table. Where are you, 95? Americum. All right, AM. And Americum is what's in your house right now, because they're in all the smoke detectors. So I can tell you about that if you're interested. Okay, I already had that as radon. Let's go here, 82.